So the Schrodinger equation can't actually be solved except in the simplest of cases, which is not, for instance, the standard cases for nuclei, trying to determine nuclear properties. And so what my doctoral research is focused on is approximating both the nuclear Hamiltonian and solving the Schrodinger equation in an approximate way. The time-independent Schrodinger equation is shown here, and it's an eigenvalue equation. The eigenvalue is the energy of a many-body system, and the eigenvector is the wave function. The nuclear Hamiltonian is given as the sum of a kinetic and potential term, and here I represent the potential term as two-body, and then it can continue up to as many particles as you have. So A will be used for the total number of neutrons and protons, so it can be up to A body. One trick to help aid in the solution of the equation is to add and subtract what's called a mean field potential, where it's a simple one-body term. And so we have a mean field Hamiltonian, H naught, which can be solved exactly. And then there's a smaller term, the residual interaction, which can be treated perturbatively. The selection of a mean field Hamiltonian gives us can be solved. And so the solution of the Schrodinger equation for neutron orbits in tin 132 with a simple harmonic oscillator mean field potential results in a shell structure shown here on the left. There's spacing between oscillator shells of 1 h bar omega, which for tin 132 is 8 MeV and is given by the total mass number of the nucleus. Experimentally, properties such as the 2+ excitation energy of even nuclei have been shown to exhibit enhanced stability for certain numbers of protons and neutrons, and those numbers do not agree with the shell closures of the simple harmonic oscillator potential. If a strong spin orbit potential is added to the mean field, the degeneracy of an oscillator shell is broken and it's split up into components. The single particle basis now has good quantum numbers NL and J, and there are new shell closures in this single particle basis, 2, 8, 20, 28, 50, 82, and 126, which agree with the experimentally determined magic numbers. They're called the nuclei, which exhibit enhanced stability. The oscillator shells can be referred to by their components in this single particle basis with NL and J. So the N = 2 oscillator shell is called the SD shell, as it's composed of the D5 half, 0 D5 half, 0 D3 half, and 1s 1/2 orbits. Likewise, the N = 3 oscillator shell is the PF shell. The large energy gap between, for instance, the P shell and the SD shell and the SD shell and the PF shell suggests that the low energy properties of nuclei in the SD shell can be reproduced solely by an interaction in the SD model space. And therefore, an effective interaction which operates only in this reduced model space can limit the amount of computation necessary to solve the Schrodinger equation. So this idea to utilize shell structure and to limit our calculation necessary is a hallmark of a theory called configuration interaction theory, and is one of the tools that I'll use. I mentioned that the 2+ excitation energy of even nuclei display enhanced stability for certain numbers of neutrons and protons. The 2+ energy is shown here as a function of neutron number for the calcium isotopic chain in orange and the silicon isotopic chain in green. For calcium, you see prominent peaks at N = 20 and N = 28, which are indicative of this type of shell closure shown here on the prior slide, n equals 20 and n equals 28. However, and I should mention that both calcium-40 and calcium-48 are stable isotopes, so these are very well-known cases which exhibit these magic numbers. However, for the very exotic silicon isotopes, the similar behavior is seen from n equals 18 to n equals 26, but at n equals 28, the shell closure is no longer seen. And in fact, silicon-42, which was only measured approximately 4 years ago, has a lower 2+ energy than silicon-40 even, and approximately 3 MeV difference from calcium-48. Therefore, when we're determining effective interactions, it's very important to know the type of nuclei which we want to reproduce, whether they're stable or exotic. When calculations are done in a reduced model space, so for instance, here on the right, I show calculations with configuration interaction theory in the SD model space using empirical interaction called USD. The binding energy differences between experiment and theory are shown in the plot, and the majority of nuclei are reproduced with this empirical USDB interaction. There's very good agreement in the masses of these nuclei, except for a small region here where theory underbinds the experimental values. Experimentally, it's been determined that for these nuclei, the higher energy PF orbits, the next oscillator shell, contribute to the ground state properties of these nuclei. And because these ground states have different configurations than expected, they're referred to as inverted configurations, and this is called the island of inversion region of the nuclear chart. And in connection to this other plot, I like to point out that this doesn't happen for the good shell closure at n equals 20 near stability around calcium-40, but only for these very exotic neutron-rich isotopes around sodium-31, magnesium-32. The reason that we're very interested in these exotic nuclei is that they are currently accessible with the rare isotope facilities used in nuclear physics. Our theoretical predictions currently are not reliable for these exotic nuclei, but it is necessary to predict the properties of these nuclei in order to So the standard formulation of configuration interaction theory doesn't work as well for exotic nuclei, and specifically the renormalization methods which produce effective interactions for use in a configuration interaction calculation do not account for the behavior of exotic nuclei and instead use always the shell structure I showed on the first slide. This is a problem because loosely bound orbits are often important as valence orbits for exotic nuclei, and they have different behavior than harmonic oscillator basis, which is generally used. Therefore, my goal was to produce a new theory, a new procedure to produce effective interactions which combine some standard techniques in nuclear theory, such as configuration interaction theory and energy density functional methods, which are very similar to standard DFT, and to use this new method to produce reliable calculations outside of standard shell model spaces, and especially for exotic nuclei. Specifically, I used these two methods as well as others in order to gain the accuracy of these CI techniques, which are the most accurate method applied to hundreds of nuclei, and to also obtain the generality of EDF methods, which can be used to calculate the properties of any nucleus. CI, however, is limited by mass. So the procedure here is actually relatively detailed, and so I'm going to put it up for people who already have some understanding of nuclear physics, but I'm just going to highlight a couple things for the general talk. So the first thing that's necessary is to choose a model space which incorporates the low energy degrees of freedom of the nuclei that which we wish to calculate. And a target nucleus is necessary in order to perform a renormalization procedure, and so this should be close. It should be in proximity to the nuclei we want to calculate on the nuclear chart, and therefore it will have approximately the same behavior, the nuclei to be calculated. As I mentioned, the harmonic oscillator basis is generally used but does not reproduce the behavior of exotic nuclei, and so a second realistic basis called Sturm-Hartree-Fock will be used as well, and I'll show a comparison between the results with these two different bases. And lastly, I'll just mention that an effective interaction is composed of two things: two-body matrix elements and single particle energies. And these single particle energies, which we obtain from a renormalization procedure, are unreliable because the interactions generally used in nuclear physics do not reproduce single particle properties very well. As a result, in order to improve our predictive power, we will often, instead of using not exactly microscopic, very theoretically determined single particle energies, we will instead use experimental data in order to constrain the single particle energies. So the first application I'll show is to the sdpf model space, which is composed of sd proton orbits and pf neutron orbits. And I will perform this renormalization procedure, two different target nuclei, one the stable calcium-40 and the other the exotic silicon-34, and I'll do this in both the harmonic oscillator and the realistic basis. As I showed on the first slide, the 2+ energy in both of these nuclei is very high. The n equals 20 shell closure, as it's referred to, is maintained as you move to silicon-34. However, the effect of the exotic silicon-34 on a single particle basis is shown here on the left. So for calcium-40, all 4 neutron valence space orbits are bound by multiple MeV. This is in the realistic basis. While for the silicon-34 exotic nucleus, the orbits are centered around 0 MeV, and the p1/2 and p3/2 orbits are very loosely bound. This plays a significant role, as we'll see in the next slide, on effective interactions that are derived for silicon-34. So I chose this model space and these targets based on a recent theoretical work that produced a new empirical interaction in the sdpf model space and found that in order to reproduce experimental quantities, it's necessary to have a piecewise defined interaction that has different matrix elements corresponding to how exotic the nucleus is. So specifically, this new interaction called sdpfu has neutron-neutron pairing matrix elements, which are reduced by 300 keV z less than or equal to 14 in order to better reproduce data. And so this is, for instance, for the silicon isotopes. As I showed on the first slide, where silicon-42 had a very low 2+ energy, this reduction enables the new interaction to better reproduce those values. I showed here values of the matrix elements on the plot for different ingredients of the renormalization procedure. So in this calculation, harmonic oscillator basis is used with silicon-34 as the target and with calcium-40 as the target. And in color, I single out the pairing matrix elements for two reasons. One is that they are very important for the properties of even nuclei. And second is that these are the matrix elements that were reduced by Novacki and Povez in the theoretical work from the prior page. In the harmonic oscillator basis, what you see is that regardless, the matrix elements lie very close along this line of equality. And so therefore, it doesn't matter which target you use, the results for the interaction are the same. And this contradicts the conclusion of Novacki and Povez, who suggested that just this change in proton number will have a large effect on the output matrix elements. That's how they justified their 300 keV reduction. However, when I do the renormalization procedure, but this time in the realistic Sturm-Hartree-Fock basis, you see here that for silicon-34 as the target, the matrix elements are reduced from this line of equality. Specifically, the pairing matrix elements, which are in color, lie further from the, lie further from the line of equality, and the reduction in the pairing matrix elements as determined from this relatively microscopic procedure is 214 keV. So that's in comparison to the empirical 300 keV that was found by Novacki and Povez. This reduction tells us that it is very important when we're developing effective interactions to take into account the type of nuclei which we want to reproduce, and that the exotic nuclei depend significantly on the basis. So this island of inversion region, which I mentioned from this picture, is another example of very exotic isotopes where theoretical predictions have not corresponded very well to the experimental data. And so I represent here on the right an example of the types of configurations which occur. So for magnesium-30, which here at Z equals 12 and N equals 18 lies outside of this island of inversion region, we can represent the behavior of the ground state of magnesium-30 as an almost fully occupied SD shell with, this is just the neutron orbits here I'm showing, an almost fully occupied SD shell with what are called two neutron holes, two neutrons missing in the SD shell. Because even nuclei have 0 plus ground states, when we add two neutrons to get from magnesium-30 to magnesium-32, which is here in this island of inversion region, we can do it in two ways. So I listed as scenario A, where we occupy these SD orbits and we close the SD shell, or scenario B here, where instead we occupy the higher energy PF orbits and have a what's referred to as two-particle, two-hole structure. And this also has a excitation of 2 h bar omega because we've put two neutrons into the next oscillator shell, which is 1 h bar omega higher in energy. So it's been found experimentally that there are many nuclei that exhibit 2 h bar omega configurations in the ground state, and all the ones in this region that have been found have n greater than or equal to 19 and z less than or equal to 13, but the experimental boundaries are not known, likely because they lie beyond our current capabilities experimentally. Therefore, this theoretical approach can enable us to determine the boundaries and to predict the properties of exotic nuclei in this region. So I use a model space with SD proton orbits and these neutron orbits. It's possible that the entire SD and PF shells are important in this region, but for computational reasons, I've excluded the lowest energy and the highest energy orbits from that model space. because, as I mentioned, the single particle energies that we determine in our renormalization procedure are not very accurate, we treat them as parameters, and we also include a few parameters for three-body forces, which aren't included at all in my procedure, and one extra parameter which serves to normalize or serves to reduce the strength of the two-body matrix elements from the renormalization procedure by about 10%. So with these parameters, it's necessary to fit the data, and the RMS deviation that comes out from the fit is approximately 370 kV, which gives us approximately the uncertainty we expect to see for calculations in this model space with this interaction that I have derived and will refer to as the IOI interaction. So here I show some general trends in this region. So I show the isotopic chains with an even number of protons, the separation, neutron separation energy as a function of neutron number. So I define here the neutron separation energy. Basically, without going into too many details, what you can see from the graph is that there's very good agreement in general between experiment and theory, and therefore, where our experimental data ends, we are able to move farther with the theoretical predictions and determine what's known as the neutron drip line, which is the last isotope of a chain that can be produced and observed. The way that that value can be read off the graph, in a sense, is that as soon as the separation energy goes below 0, you have an unbound isotope. Because there's also something called a 2-neutron separation energy, which is important in this region, if the separation energy, 1 neutron separation energy here is positive, but the nucleus is still unbound, then I plot the 2-neutron separation energy with a dot. So what you see is that oxygen 28 in this procedure is bound, and so as calculated, the last isotope of oxygen that can be produced is oxygen 26. Experimentally, it's known that oxygen 24 exists and oxygen 25 is unbound, and it's expected. There's some experimental evidence that suggests that oxygen 26 is unbound. But basically, we can move forward and we can see that neon 34 is the last isotope of neon that can be produced and detected experimentally, and so with other isotopes here in this chain. In addition to general schemes, we can also look at level schemes of specific nuclei. So I show here experiment on the left and calculations on the right. The binding energy relative to the core of our model space, oxygen 22, is shown for the two calculations. And what you see is that there's very good agreement between the levels that are known experimentally and the calculation. So the 0+ ground state agrees within about an MeV. The 2+ state here is right on target, and then we can do pretty much a 1-to-1 correspondence up until above 5 MeV. So there's actually 2 states here, and they correspond to these states here. This is for a stable isotope, which is in the model space, but it's not in the island of inversion region. So when we go to the island of inversion region, one of the problems is that these are very exotic nuclei. There's less data. So for instance, neon 32 is in this region, but only a 0+ and a 2+ state are known, and these are reproduced relatively well. However, there's a very large level density seen above 2 MeV, theoretically, which has not been observed experimentally and is above the decay threshold here. So one nucleus in the island of inversion region which has significant data is magnesium-31, and I show here the calculation for that. The binding energy is in good agreement, while the ground state spin is 1/2+ experimentally and is 7/2- theoretically. However, the very high level density below 500 kV is reproduced. These 4 states are actually included in the fit and therefore come in to the 370 kV RMS deviation explicitly. The result of this work is that we can look at the ground states of the nuclei in this model space. So there are 100 nuclei here that I've calculated. The stable isotopes are shown in the black boxes, and the color, what is plotted here, the color corresponds to the h-bar omega excitations of the ground state. So what that means is that something with 0 h-bar omega excitations fills in the standard way, and the island of inversion is represented by the orange, red, and yellow boxes. So theoretically, we see that the island of inversion extends from approximately n equals 19 all the way up to n equals 24 is the farthest shown here, and almost all isotopes with Z less than 13 lie in this region. So what this suggests is that, although it hasn't been determined yet theoretically, or excuse me, experimentally, is that the island of inversion extends much farther than has been determined as yet. So let me skip this last one and just put up a summary that the realistic basis is important to use when we're creating effective interactions to produce calculations of nuclei, especially because a realistic basis will have a better description of loosely bound orbits which extend much farther radially than the harmonic oscillator basis. And this harmonic oscillator basis, if it's used, results in a stronger interaction and therefore in overbinding as we do calculations. So it's important to use a realistic basis, and when we do calculations in the island of inversion region in a very exotic region of the nuclear chart with an interaction derived from a realistic basis, we see that we can agree relatively well with available experimental data. And so with that, I'd just like to thank you for your time and thank Krell for the fellowship and support.